Okay, if it's a magnet, then another wire could be a magnet. So that two wires should attract each other because magnets attract each other. Simple, smart idea. So that's what this is. We have here, I'm going to pass current through these two wires. The interesting part is that I can pass the current through them both in the same direction or in opposite directions. And so let's see what happens. I'll pass in one direction. You seem to push apart at first, right? You see that? Slow down, folks. Let's see, try to catch the first motion. Yeah, it's apart, right? Repulsion. Okay, so that's like we've created two like poles and they repel. Here, I'm going to reverse the current. One is going up, and that was attractive. So here I've somehow created two like poles, or unlike poles, and they've attracted each other. So that's Ampere's experiment. So wires carrying current, not static charge, must be a current. They act like magnets. They'll attract each other. Depending on the direction, they can repel. That's it. That's the basic idea. I have another demo that I'm not going to do here. So here you get, this demo would show poles. See, there we showed first we showed a current acting on a pole. Then we showed two currents acting on each other. Then we could show a pole acting on a current. Maybe I'll do that next time. But then I want to continue with this comparison of the electricity story with the magnetism story. And the important thing is that we can do a similar thing, match the formulas one for one practically, where we substitute for the sources. See, in the electric case, the sources were Q2 and Q1. And we broke that down into Q2, and Q1 was creating the field. Q1 was creating the field. We're going to break the magnetic force down. The sources, it'll turn out, are currents and a certain length of current, like I1 and DL1. So it'll be a current and a length through which it's passing. That's going to be the source, comparable to a point charge. And then you can see that you have the other side of it. You'll have two of such elements acting on each other, inversely as the square of the distance. Now you can chunk off, as we did here, what is caused by one of the currents elements. So I wish I had more room on the bottom there, but we'll do the same story here. We're going to have the magnetic force. And it's there'll be a constant, which I think we'll call mu0, say. And then we're going to have a current element, I1, L1. And we're going to have another current element, I2, L2. Is that how I did it? Let me keep it. Yeah, I2 is going to be the source field. And so these will be the sources. And the problem is that this is a vector product. This is where the complication sets in, right here. And then I divide all of this by the usual 4 pi r squared. And then I'm going to break this part off and call that the magnetic field due to the charge element 2. And I'm going to say that the magnetic force, is mu0 times this element I1, L1 times the B produced by that. So if the thing works, it works so nicely here, they try to make it work here, and it succeeds with the complication that it'll turn out that these are all vectors. And this field here is a vector, and that's a vector. So it complicates it somewhat. So these are in the notes, and I just put it in front of you because we're going to derive some of these things as we go along. But I want you to just see the beautiful similarity, the parallelism of the two approaches. Fortunately for us, it's pretty simple. There's another slide here where we were able, on the electric side, to do something with Gauss's law. That is, we integrated the electric field over a complete surface, and we found how much charge was inside. Now, because there are no magnetic monopoles, you can't find a single source inside. So it will be that this surface integral of B over a surface will always give you 0 until we find a magnetic monopole. And then we can say, yep, there's somebody inside, one person inside. But they always come in pairs in the case of magnetism. Now, we didn't do this much in class, but the conservative field can be represented by what's called a line integral, integrating around a loop. We're going to need something like that. But we had a dipole moment for electric. We're going to have a dipole moment for magnetic. We had a torque on an electric dipole, P cross E. We're going to have a torque mu cross B. We had a field due to the electric dipole, which varied inversely as the cube of the distance. And we will find that we have a magnetic dipole, which varies inversely as a magnetic dipole over the cube of the distance. So there's a beautiful parallelism. If you didn't get electricity, as I say, if you didn't get electricity the first time, you'll see it again with just B's instead of E's and things like that, just transformed a little bit. And so the man who, there were two of them actually, Biot and Savart in France, who did this experiment where they actually tried to find, if you had a wire and another wire, what is the force between those two wires, if there's a magnetic force. And so you have I1 and I2 flowing in two different wires. And again, you can break it down by saying that the field of this I1 and this little element here, DL1, the field due to that is going to be mu0 I1 DL1 over 4 pi r squared. Now the complication is, as I said, is with these angles. And here, to find the direction of the field produced by this little element here, you have to use what's called the right-hand rule. There'll be a lot of rules using the right hand to give us directions. In other words, if you have a current like this and it's traveling in this element here, and you ask for the field at some point r, if the current is in this direction, the right-hand rule is you point your thumb in the direction of the current, and your fingers will wrap around the way the field goes. So the field will go underneath, around, over, this way, like that. Oh, I'm wrong. It's actually this. Wait a second. Yeah. If here's the current, I put my thumb this way, my fingers wrap around this. The direction of my fingers tell me which way the field is going. So in this case, the field, if the current is going this way, the current, oh, here's another little trick. We think of this as the head and tail of an arrow. So this we represent by this, and this we represent by that. So, for example, if I had the current going into the blackboard, let's say, then the magnetic field will be going around in this direction. It's a little hard to draw, but the current in that direction, the right-hand rule says the magnetic field goes around in loops, and it falls off as 1 over r squared from a small element. dl into the blackboard. Okay? So that's the complication of magnetic fields. Even if you have an element source here, the field that it produces is not radial. It's at this peculiar cross distance. So you have R, the current going into the blackboard, and the field will be running around that way. So B, you have I cross R. This is its cross product. And that is the direction of B. You remember the cross product? Are you familiar with that? The idea is so hard to demonstrate. Let's see. Let's say this is the direction of current into the blackboard. That's I. My distance R is that way. So if I take I, cross on R is that way, I point my fingers in the direction of R, and it will tell me which my thumb then points in the direction of the magnetic field. Okay? Okay, so that is the analogy, and that is the feeling we get for how the magnetic field is. Then the nasty part is that when we want to find the force, we have to get the second element, I2, L2, and it has to cross product with the B. So this gets really nasty. So for example, in the case of these wires, let's see. Let's say we have these two wires, and let's say the currents are going parallel to each other. So we pick one of them to be the source and one of them to be the pushy, the one that's being acted on. It doesn't matter what you choose. In this case, they're symmetrical. But here, you find the current. You find the direction of the field by putting a thumb here. The field at I2, because this is this way. Field at I2 is going into the blackboard, right? Then the direction of the force is when you multiply I2L cross with this one. Now I2 is this way. The current is going in this direction. So I turn I2, the order matters. You've got to start with I2, L2 first, cross it into the direction of B due to number 1, or I think I call it A, and then you get a force going this way. This is the force of B on A. So this says that if the currents are going parallel, it's attractive. If you switch the currents, let's say I switch one of them. Let me switch, to make life easy, let me switch this one so that I keep the field the same. So now I switch the currents. The field due to this one is the same. This is B due to A. But now the current is going the other way. So if I point my fingers in the direction of B, no, it's I cross B, so I have to put my, here's where it gets tricky. I put my fingers in the direction of I. That's what I do first. And then I turn the palm toward B. So here's my current going down. The B is into the blackboard, and the force will be sideways this way. So this is the force of A on B. I don't know what notation I use. Did I call this A and that B? This is the force of A on B. I don't remember what I used. But in any case, the force, when the currents are going in opposite senses, the force is repulsive. And this is the explanation why. It's always fun when people take exams and you see guys doing like this and this and this. You know, it looks like a class of a bunch of sick people. But you have to do it. You have to point in different directions. Yes, sir. Yeah, this is a very, very good question. First, you start out with one of the wires and you find out which way its field is the source. Is that okay? I found this one. I found that its number, whatever I call it, A, is pointing that direction into the blackboard. Now I have a current going this way. And the direction of the force is I point my fingers in the direction of the current, turn it in the direction of the field. So I point my fingers in the direction of the current, and I turn it in the direction of the field, which is into the blackboard, and my thumb points in the direction of the force. Same story here. This is causing this field into the blackboard. The current is going now downward. I turn it in the direction of the force, the field rather. Yes, you can dislocate. You point the fingers in the direction of the current. The field is into the blackboard. I turn it in the direction of the field, and my thumb now points in the direction of that force. That's what we have. It takes a little practice, but you can get it. Yes, ma'am. I never really told you which direction the currents were going. All I did is attraction and repulsion because it's a complicated circuit, but I do believe that's how it'll work out. We have, let's see, 5 more minutes. Do I have any time to show anything here? Okay, that's a very important rule. And this next example explains all this. Oh, it shows, for example, an application of the Biot-Savart formulation, which may look familiar to you. That is that you could, if you had a long straight wire, how to find the magnetic field at a point off the wire, let's say a distance y. And what you can do is add up the fields from all the different elements here, DL1, DL2, symmetrically. This may remind you of what we did in electricity, where you can symmetrically place charges and add up the fields, and you can do that, integrate over from minus infinity to infinity. All the little elements are going to produce a magnetic field over here. Let's say the current, let's just for fun get the current direction. The current will be coming out of the blackboard here and going into the blackboard here, right? At least that much we know. And you can actually calculate this by adding up all these different elements, and you get the formula analogous to the formula we got for a charged wire or charged line of charge. You can get a line of current. You can get the field. I'm not going to do the integral. I didn't do it in electricity. I'm not going to do it now because there's a simple way of doing it. Just like it was a Gauss law where with the line of charge we put a cylinder over this and we were able to get the field very simply. There is a comparable law in magnetism which will give you the answer to a problem like this very simply. So I'm not going to knock you out with doing integrals over this thing. We'll just go later on next time to this law which in a couple of steps, very easy steps, you can find the magnetic field around the line of charge or line of current in this case. So, but I just want to show you that this is the same kinds of steps that we did in electricity. You can do here. You just add up a little bit of the sources to give you the total field. Oh, this is a great little demo here that you're going to need in your lab. And that is to show that how a magnetic field, if you put a magnetic field, the force acts perpendicular to the field and the current. Because if you have a current going one direction, and we have a field going in this direction, the current times the field will give you a force this way. Now what we've done here is we put two electrodes here. We're going to have an electric discharge of electrons going from, well, if this is plus, the electrons are going this way, but the current is going this way. We put on a field, we'll deflect. See, the current is this way. The field will be this way. And the force will be this way because you get current times field, give you force this way. So some of the charge will go onto these electrodes and produce a voltage here. Sideways voltage. See, the current is going this way, but we produce a sideways voltage. That's called the Hall effect. You'll be using such a probe. It's a way of measuring how strong the field is. So let me turn this guy on, turn this guy on, turn this guy on. Okay. Okay, now, see, we've set it so that 6 is actually 0. 6 is actually 0. Because we're going to go plus and minus, and there's no minus on this particular meter. So we've offset it by 0. Now I'm going to bring a north pole, so the lines are going to go this way. And you can see the glow here, maybe? Yeah. Is there any point here? Oh, that's pretty. Okay, I don't know if you'll be able to see it deflect. No, we'll do that next time. You can actually see this beam deflect. Well, what you can see, if I bring the magnetic field here, right now it's reading about 6. If I bring it here, if I deflect the beam, the electrons hit one of those electrodes and produce a voltage on it, proportional to the magnetic field. So it's a way of measuring the magnetic field. Let's see. You tell me, I'm going to keep my eye on this. Anything happening? Okay, that's with the north pole coming there. Which way did it go? Positive? Okay. Now, in principle, if I turn it around, the force should deflect the thing the other way. That's why we said it's 6. Okay, sideways motion, sideways voltage. So that's the Hall effect, which was not named that because somebody did it in the Hall. There was a man named Hall who discovered this effect. Okay, so you'll be using that in a small device in your lab. Not a tube, but a solid. All right, how'd it go? Get that? That's good.